In these examples, we take a look at hypothesis testing for one proportion. Recall that proportions are the data values that correspond with categorical data. If we were counting the number of times that we get heads out of 10 coin flips, we would have something like 3 out of 10 or 4 out of 10, and that would be our proportion counting the number of heads, because heads are categorical data. Now that we have a method for analyzing data, we will set up hypotheses to test our theories and claims. Last week, Professor Caldwell told me that she believes that more than 80%, or 0.80, of Umoja scholars see an academic counselor each semester. How can we test this claim to see if it is true? We set up the following study to test the claim. So I've highlighted here our research question that we are investigating. So that question is, do more than 80%, or 0.80 in decimal form, of Umoja scholars see an academic counselor each semester? So when we do a hypothesis test, we have to set up rival claims. We call those claims the null hypothesis and the alternative hypothesis. We always state the null hypothesis first, and our notation we use in statistics is H with this 0 in the subscript. The 0 represents no change, and that's why this is called the null hypothesis. Null is a term that means nothing. So the nothing changes hypothesis. And so that says the proportion of Umoja scholars who receive academic counseling is equal to 0.80. With symbols, and very often we'll write our hypotheses with symbols to save time, we say H sub 0, and then typically we put a colon here. P equals 0.80. So that P is our population proportion of all Umoja scholars who see an academic counselor. So we have to define what our P is. Notice it's not a P hat. That would be if it was a sample data. So we're always making a prediction about the whole population. So when we write our hypotheses for categorical data, we always just use P standing for proportion. The alternative hypothesis, which is our competing claim, and we notate that with H with a subscript A, and it doesn't matter if you use lowercase a or capital A. You'll even see that I sometimes interchange with a lower or capital A. People sometimes also put a 1 here, like 0 versus 1 as the two choices. We'll use H sub A in our class. And so that alternative hypothesis says the proportion of Umoja scholars who receive academic counseling is greater than 0.80. Or with symbols, we'd say HA with a colon. P is greater than 0.80. So I said these are competing claims because they can't both be true. So if the proportion for the population is equal to 0.80 of Umoja scholars who are seeing an academic counselor, then it couldn't be true that the proportion is more than 0.80. And vice versa. If the alternative hypothesis ends up being what we think is true, then it couldn't both be true that you have more than 0.80 or more than 80% and equal to 80%. So you always want to set up your hypotheses so that they are competing. So that means when we do our alternative hypothesis, we always use greater than, but not greater than or equal to, or less than, but not less than or equal to symbol, or the not equal to inequality, but we don't have any sort of equality possible when we write the alternative hypothesis. So we want to know, well, what's the claim? So the claim here is that more than 80% of Umoja scholars see an academic counselor each semester, and this claim corresponds with the alternative hypothesis. So anytime we're investigating a research claim, we set that claim up as our alternative hypothesis, and we set our null hypothesis up with equality. Question B asks, in the null hypothesis statement, what do we assume to be true about the population? So in our null hypothesis, we assume the population proportion is equal to the given value 0.80, and the null hypothesis always has that equal sign. When we enter our hypotheses in StatCrunch to have StatCrunch do the calculations for us, we put in the 80% as 0.80 in decimal form, so that's one reason why I'm writing that here in decimal form. When you're writing by hand, it's okay to use decimal or percent, whichever you prefer. So in the alternative hypothesis statement, how are we comparing the true parameter value that's unknown to us? So in this case, that's that population proportion that's unknown that we're trying to make a prediction about, to the value we assume true in the null hypothesis. So in this claim, in the alternative hypothesis, we use the greater than inequality. The two hypotheses here, the null hypothesis, H sub 0, and the alternative hypothesis, H sub A, are competing claims. And again, we use this shorthand H sub 0 and H sub A just to save us having to write out the words null hypothesis and alternative hypothesis. You're welcome to write the words out if you prefer instead. I think you'll find that you like the shorthand. I definitely find the shorthand much faster when I'm doing my write-ups. So here are some general observations about null and alternative hypotheses. So the hypotheses are competing claims about the parameter or about the comparison of parameters. So I underline parameter here because the parameter, it could be a population mean or it could be a population proportion. So in this section, we are going to look at population proportions, but know that later on we'll look at population means for quantitative data. So we can make these same kind of hypotheses claims for quantitative data as well. But for now, we're going to focus on categorical data. Both hypotheses are statements about the same population parameter or same two population parameters. So if you look back at how we wrote those claims, they're both talking about the same P representing the population proportion of all Umoja scholars who see an academic counselor. So we wouldn't switch populations between the two hypotheses. Both hypotheses are about that same population of students in this case. The null hypothesis is always going to have an equal sign, so that'll help you in writing your null hypothesis. We think about that as no change, so things are equal to the value that we're investigating. And then, so that they're competing claims, the alternative hypothesis is always an inequality statement. It contains a less than or a greater than or a not equal to symbol. In a statistical investigation, we determine the research question and thus the hypothesis before we collect data. If we collected our data and then tried to look back at our data and come up with a hypothesis, that would be biased. And so we say that's, you might be tempted to cherry pick your data or make a hypothesis based on the data that you collected. And there could be some error or bias in how you collected your data that influences your results. So we always want to start with our hypotheses and our research question, then determine our data collection plan. So there's 4 steps to the hypotheses testing process. Step 1 is to determine the hypothesis, and the hypotheses are written based on our research question. Step 2 is collect the data. So ideally we select a random sample from the population. The data comes from that sample, and then we calculate a statistic. If it's quantitative data, we'll calculate a mean. If it's categorical data, we'll calculate a proportion to summarize that data. So we start making a claim about the population, and then we go get some data. So that sample data is going to be a sample proportion or a sample mean, because we know we can't get a sample of the whole population, so we take a random sample of the smaller subset from the population. Then we assess the evidence. So by default, we always assume that the null hypothesis is true. In a court case, you would say you assume somebody is innocent until proven guilty. So the null hypothesis is similar. We assume it's true until proven otherwise. Could the data come from the population described by the null hypothesis? Use a mathematical model to examine the results from random samples selected from the population described by the null hypothesis. Figure out if results similar to the data are likely or unlikely. Note that the wording likely or unlikely implies that this step requires some kind of probability calculation. So this is where we're going to bring in our 68% likely, 95% likely, 99.7% likely, and whatever percent we want to use from earlier calculations in this chapter. Our last step, step 4, is to state a conclusion. So we use what we find in the previous step to make a decision. So this step requires us to think in the following way. Remember that we assume the null hypothesis is true. Then we have one of 2 outcomes that could occur. The first, one possibility, is that results similar to the actual sample are extremely unlikely. This means that the data do not fit in with the results from random samples selected from the population described by the null hypothesis. In this case, it is unlikely that the data come from this population, so we view this as strong evidence against the null hypothesis. We reject the null hypothesis in favor of the alternative hypothesis. So notice this language we use, rejecting the null hypothesis. It's our way of saying it's unlikely the null hypothesis is true with data like what we've observed. So we say we're rejecting it and we're going to choose in favor of the alternative hypothesis. Really similar to how a jury makes a decision in a court case. The second possibility The other possibility is that results similar to the actual sample are fairly likely, not unusual. This means that the data fit in with typical results from random samples selected from the population described by the null hypothesis. In this case, we do not have evidence against null hypothesis, so we cannot reject it in favor of the alternative hypothesis. So this is like the situation where someone is tried for a crime in court and there's not enough evidence to say they're guilty. So we don't say that person's necessarily innocent, although they get set free. And so it's similar with the null hypothesis. We don't have enough evidence against null hypothesis, so we're stuck with assuming that it's true, but we don't say for sure that we have good evidence to support it. We just say we can't reject it. In this example, we're going to look at how hypotheses tests for proportions look graphically, so they can be visualized as one-sided or two-sided on the graph. Recall we named the area and the distribution tails to the left or the right of the z-score the p-value, and that's a capital P. I know there's a lot of p's floating around here. So that's the probability, and we say the p-value is the likelihood of results like the observed data in our sample if the null hypothesis is true. So depending on the alternative hypothesis we are testing, the hypotheses test can have a left tail p-value. So that's our first picture over here. And you can see the alternative hypothesis is saying p is less than some value p sub 0. So p sub 0 is whatever number we want it to be. It's the proportion we're comparing, and it's going to be between 0 and 1. So in our Umoja Scholars example, that value would have been 0.80. And so if we're doing a less than comparison, depending on where we end up in the normal distribution in terms of standard deviations, our p-value is going to be the area on the left side of the graph. The second picture shows a right tail p-value, and that comes up when we're using a greater than inequality. So if we say our proportion is greater than some value, then we're looking just at the right side of the graph for that area, and that area is what we call our p-value, and that capital P is for probability. I know there's a lot of p's floating around, so we try to keep the capital P for the area or the probability of the normal curve, and when we talk proportion, we try to use lowercase p. Unfortunately, this segment of statistics class has a lot of words that start with p. The last choice is a two-tailed p-value. So in that last picture, we see both sides of the graph have tails because our alternative hypothesis is using the not equal to inequality. So if we use the not equal to inequality, that's saying we don't know if the values could be greater than or less than, so we're leaving both tails of the graph open, and we call that a two-tailed p-value. So, and then there's a note here in the graphs. Note that the lowercase p represents the unknown population proportion. Lowercase p with a sub-zero represents the value we're comparing to. So in our previous example, that was 0.80. It could be any value 0 to 1. And then when we're setting up the hypothesis test, we choose that value for p0. So for example, if you are comparing to 50% or 0.50 as a decimal, then you would use 0.50 there. You don't put in the default p sub 0. You put in whatever value you're comparing to. So in examples A and B for each of the following scenarios, define the population proportion, write the null and alternative hypotheses, and explain if the hypothesis test will have a left tail, right, or two-tailed p-value. So question A says, in a taste test, participants are comparing Pepsi to another cola drink and determining which drink is sweeter. The scientists planning the study claim that more than 65% of participants rate Pepsi as sweeter. And I highlighted that claim that more than 65% because that's going to help me write my alternative hypothesis. So the first thing I want to do is define my proportion. So I say here lowercase p is the proportion of all people who rate Pepsi sweeter. So my null hypothesis has to have equality in it. So I'm going to say the proportion is equal to 0.65 since we're using the 65% value for our comparison. So my null hypothesis h sub 0 is p equals 0.65. In our notations, we usually put a colon after the h sub 0 just to separate it from our hypothesis part there. And then my alternative hypothesis, h sub a, is that the proportion is more than 65%. So I write p is greater than 0.65. And then since we're using a greater than inequality, if you look back up at our picture, you can see we're going to be thinking about the area on the higher side of the graph. So this will be just a right tail p-value. Question B. A company claims that 80 out of 110 workers report themselves as highly satisfied with their jobs. Consultants have been hired to investigate whether the true ratio of highly satisfied workers is actually different from this ratio of 80/110. So notice I highlighted here actually different from. So I'm not told if there's a greater than or a less than relationship, a more than or less than. So if I just have that they're looking for something different, then I know this is where I use that not equal to inequality. So I first define my proportion. So here P is a proportion of all workers at the company who are highly satisfied with their jobs. And so my null hypothesis says that that proportion P equals 80/110. We always have equality in the null hypothesis. My alternative hypothesis says that proportion is not equal to 80/110, and I'm using the not equal to symbol here, the equal sign that's crossed out, to leave me the options of having a less than relationship or a greater than relationship. So we say this is a two-tailed p-value because we're using the not equal to inequality, and we could be on the low side of the graph or on the high side of the graph. So we would count both of those areas when we're figuring out our probabilities here. Okay, in the next examples, we're going to see how to use StatCrunch to actually go through some probability calculations with the normal curve.